Sudha.
Good morning. Can you hear me?
Thank you for joining this meeting.
It's my pleasure. Thank you very much for inviting me, Prof. Sudha.
Thank you.
Good morning to all. I welcome you all for the day 3, session 5 of the virtual international conference on hierarchically structured materials organized by Department of Physics, SRM Institute of Science and Technology, Ramapuram campus, Chennai. Now I welcome our resource person, Dr. Mohammed Faiz bin Mohammed Salih, Senior Lecturer, University of Malaya, Malaysia, for his invited talk. And now I request Dr. A. Nadraj, Assistant Professor, Department of Physics, to introduce our resource person. Nadraj, sir.
Yes, ma'am. Yeah. Welcome you all for the third day of virtual international conference on hierarchically structured materials by Department of Physics, SRM Institute of Science and Technology, Ramapuram campus. I'm happy, privileged to introduce Dr. Muhammad Faiz bin Muhammad Salik, Senior Lecturer, University of Malaya, Malaysia. Dr. Faiz Salik is currently a senior lecturer at the University of Malaya, Malaysia. He graduated with a Bachelor of Engineering and a Master of Engineering in Electrical and Electronic Engineering from Shizuoka University, Japan, in the year of 2009 and 2011, respectively. He obtained his PhD degree in Nanovision Technology field in 2014 from Shizuoka University. He was a research fellow of Japan Society for the Promotion of Science from 2011 to 2014. He was also a postdoctoral researcher at Research Institute of Electronics, Shizuoka University. Before joining the University of Malaya in 2015, his research interests are in energy conversion materials, materials and devices, with a focus in thermoelectric and in development of thermoelectric characterization system. He has published more than 50 scientific articles and made more than 100 presentations at national and international conferences on the uh, aforementioned research topics. He also active in developing and promoting thermoelectric researches in Malaysia and was elected as a vice chairman for Malaysian Thermoelectric Society. With this credential, I invite Muhammad Faiz bin Muhammad Salih to deliver a talk, thermoelectric power factor of reticle-based titanium dioxide thin film. I welcome you, sir.
Okay. So good morning, everyone. So thank you very much. First of all, I would like to express my gratitude to the Department of Physics, SRM Institute of Science and Technology, for giving this such opportunity to share my research in this wonderful virtual international conference, ICHSM 2021. So I hope that I can give some benefit sharing with you all related to thermoelectrics field. So before I start my presentation, so I would like to share my slide. So please wait a moment. So if everyone can see my slide that I have shared.
Yes, sir.
Okay, so thank you very much. So again, I would like to express my deepest gratitude to the Department of Physics for giving me this such opportunity to share my research related to thermoelectrics with you all. And then I would like also to express my gratitude to my fellow collaborators from University of Malaya, University Tun Hussein On Malaysia, Indian Institute of Information Technology Design and Manufacturing Kanchipuram, and also from Shizuoka University. So for today's topics, I would like to share our research related to thermoelectric power factor of rutile phase TiO2 thin film. So this is my outline for today's sharing. So the first in my sharing, I would like to introduce a little bit on the electricity consumption, buildings, thermal management, and self-powered smart window. Since our research, we are focusing on the thermoelectric application, especially for the usage of this so-called self-powered smart window. And then I would like to introduce our research background, especially on the thermoelectric device. And then I would like to focus on the TiO2, the titanium dioxide, as a smart window material and also as the thermoelectric material. And then I would like to discuss a little bit on our progress related to that TiO2 as the thermoelectric device for this smart window material application. And if the time is permissible, maybe I would like to also to share a little bit about our university. So I'm planning to share two videos related to University of Malaya, and I hope you all can gain much benefit in this sharing session. Okay. So for the first part, since we are using the thermoelectric, so mainly when we say about thermoelectric, we have many kind of application, and mainly of us are focusing on generation of electricity, also called the thermoelectric power generator. So when we look on the power consumption in our society or in our world right now, so especially in Malaysia, so mainly, the electricity consumption is consumed by the residential and commercial. So if we look the data in Malaysia, for example, in 2008, we used around 72 terawatt hour for that residential and commercial. And then after 10 years, 2018, so it's increased around 18 terawatt hour, becoming to 19 terawatt hour. And then if we see that this energy mainly come from the thermal energy generation, which is the conventional one that we use coal, we burn coal, and then we use the Rankine cycle to generate the electricity. And we know that we consume around 7,774 kiloton equivalent of burning the crude oil. So it's quite a lot. So if we see here that 100% of that energy consumption is mainly on that building energy consumption from this residential or the commercial energy use in a specific country or in our society. So in these 10 years, this energy demand become increasing and increasing years by years. So for example, if we look in the world energy consumption, the United States, for example, it consumes around 19% from the total world energy consumption. And that from that 19% is almost half of that, which is around 41% is used by the commercial and residential energy consumption. And if you see how we generate this electricity, so mainly we are using the coal, natural gas, nuclear, and so on. And it's a little bit on the renewable energies. So for the thermoelectric power generator, which is so-called this kind of renewable energy, which we convert the temperature difference into electricity. And if we see more detail about the usage inside the commercial and residential, so we can see that half of that energy are using to space heating and also to space cooling, which is around 47%, so half. So if we can reduce this power consumption to heat the space or the room inside the building, or to cool or inside the room or the building, so we can reduce almost half of that power consumption that we consume inside our society. So maintaining the thermal comfort in building is quite a bigger challenge, and it's a very important or a good approach for for us to improve or to decrease the energy consumption in our daily life. So if we see inside the building thermal management, we know that we can have many kind of interaction between heat outside and inside the building. For example, we can have the increase of the temperature inside a room, for example, in this picture. So we can have from the solar gain, which is the radiation heat from the solar or the sun. And then we can also have the heat conduction between the rooftop or the building itself. And then we can also have the heat interaction between the electrical appliance such as the lamp, the television, and also ourselves. So this kind of heat can contribute or can increase the demand to control the temperature inside the building. Either we want to heat the building or either we want to cool the building. And one more is if you look here, the most weakest, and it reported that windows are the weakest part of the building component because and then over 50% of the building heat is transferred occur this window. So we can see that that the heat can be transferred through the conduction or through the radiation movement of the heat by infrared energy through the glass or the direct transfer of the heat through the window itself. So if we can improve the window, so we can improve the thermal management inside our building. So this why we said that the windows are the weakest part of the building because it has the low thermal performance. So due to that conduction or the radiation heat between outside and inside the building, and it has the high maintenance because as you all know that the window can easily become dirt, so we need to clean it every day, for example. And then it is also the inefficient component because it just helps us to connect us with the outside world, or we can see transparent, or we can see through outside by using the window, and also to let the light going inside our room or our building. So if we can improve this advantage of the window component inside our building, so we can improve the electricity consumption that I just mentioned, that almost 50% of the electricity consumption for residential and for the building is mainly come to heat or to cool the room or the building itself. So there is one approach to overcome this inefficient window, which is by introducing the smart window. For example, this company have, as we all know, that we have the conventional already in the market, which is the smart window can reflect the heat or the UV light that can help to reduce the thermal management or to improve the thermal management inside the building. So they use a glass and then they put some thermal insulator, or we call the reflection layer. So this can allow the natural light to come in and it can reflect back the solar heat or the UV rays. So if we use this kind of smart window, it is reported that we can reduce the energy cost by up to 50%. And then if we look in detail about briefly about the type of this kind of smart window, so in general, we can have three kinds of smart window. The first one is the electrochromic smart window, and then we can have the thermochromic smart window, and we can have the photochromic smart window. So for the electrochromic smart window, we are using voltage or current to control the optical properties of the material to let in the light and to block the heat or the UV rays. For the thermochromic, we are using the temperature. So when we increase or we reduce the temperature environment of that window, we can change the optical properties of that thermochromic layer. And for the photochromic smart window, they are using the UV light to change the optical properties of that photochromic coating or the layer to allow the natural light to come in and to reflect back the solar heat and UV rays. So if we look on the disadvantage and advantages of this kind of photochromic, thermochromic, electrochromic smart window, we know that for the thermochromic and photochromic, we don't need to have external power supply, so it can be used by themselves. We don't need the external power or external work. If we use the electrochromic smart window, so we need to have the external power. So instead, we want to reduce the power consumption. We also need to use the electricity to make that electrochromic to work. So it's much better if we want to improve the thermal management or to by reducing the power consumption usage. So it's much better for us to use that photochromic and thermochromic. However, this photochromic and thermochromic, so we cannot control the optical properties freely because it depends on the surrounding temperature for the thermochromic and also how much the intensity, for example, the UV rays that come in. So there is advantages and there is disadvantages. So it's depend on our focus. So if we want to reduce the power consumption, so we need to have the smart window that can operate by itself. So the researcher have also introduced this so-called, we call it the self-powered smart window. So as I said that the smart window can reduce the energy cost by up to 50% if we integrate that smart window with the kind of energy harvester devices. For example, like the solar cell in this picture, there are several researchers show the integration of that smart window with the solar cell. We can have a potential energy saving up to 50 to 70%. So it's quite a lot. So if you recall back, we need to use around 50% in order to manage the thermal inside our building or in our room. So if we can reduce this, imagine how much we can reduce the power consumption that we are using in daily life. So this kind of integration of the smart window with the energy harvester devices will enable harvesting of the solar energy, act as a transparent insulation layer, and also control the solar radiation transmission and inner glass surface temperature. So as I said before, if we use only the thermochromic or the photochromic, we cannot have the freely to control the optical properties. But if we use the electrochromic, we need the external power supply. So if we integrated with this kind of energy harvester, so we can also have control on the optical properties of the material. And this kind of integrated device, we call it as the self-powered smart window. So this is the example of the integration device with the energy harvester. So just I mentioned that some of researchers are integrated that with the photovoltaic or the solar cell. So change from the photon energy into electrical energy. And some researchers also use triboelectric nano generator where they put some piezo electric component where they change from the mechanical energy. For example, if we use in the window, we have the wind, we have the raindrop, we have that mechanical energy that can be converted into electrical energy. So there are also some word that we call the multifunctional smart window. So as I mentioned before that window is the weakest component inside the building. Why? Because it need one is the maintenance. So that's why people also build this kind of function through that smart window. So we have several layers. So we have the glass, we have the thermal responsive material layer, we have the integrated layer, and then this we call it as the smart window. So the smart window is not only can block the heat or the UV light, but also can generate or harvest energy by the integrated layer and also have the ability to self-cleaning and wettability. So this kind of multifunctional smart window of the structure can help a lot to improve the functionality of the window in order to reduce the power consumption or to improve the thermal management inside our building. So if we look in the thermal responsive material, we can have many kind of material that can be used. For example, like the hydrogel, ionic liquid, metamaterial, perovskite, liquid crystal, vanadium dioxide. So the conventional one, we are using the vanadium dioxide together with the titanium dioxide. So just I mentioned that this kind of multifunctional smart window, so we can have the self-cleaning and wettability. So visible transmittant performance is important, and also how well we can repel the water at the surface of the window. And then integration with the energy harvester. So the most important is the energy conversion performance. For example, we know that the solar cell has a quite high energy conversion performance that can be applied in daily life. And then the combined electrothermal technique, because we know that just I mentioned, if we use only the thermo or the photochromic, so we cannot have freely control on to control the optical properties. So we need better to combine with the electrochromic material. So that's why we can control the optical properties. For example, if we want to change the light to come in, to come out, or the heat to come in, to come out, we can freely switch on the switch off the devices. So that's why we need this kind of combined electrothermal technique. So we have some suggestion. So we would like to integrate that self-powered smart window with that thermoelectric device. Why we said so, or why we suggest this kind of approach, because we know that thermoelectric device work to use the waste heat to change into electricity. So this in indirectly can improve the heat management, because we are using the heat to change it into electrical power energy, and then we also can increase the harvested energy. So we can have two benefit instead of just use it just for the energy harvested. So as we all know that this thermoelectric device, the TE device, use the apply heat or the waste heat to convert the temperature difference into electrical power or the electrical energy. So we know that when we have temperature difference, so this thermoelectric device can convert it into useful energy, which is the electricity. So if we imagine back the window, so we can have a temperature difference between the outside and inside the room or the building. So we can harvest the energy from that temperature difference. In general, this thermoelectric device, we can have two types. Either is a thermoelectric, which is based on the solid state material. Usually we are using the semiconductor, and if you are familiar, we have two kind of structure where we call it a pi structure, that we have two type of semiconductor, N and P type, in order to increase the voltage that we can obtain from that thermoelectric, that so-called the thermoelectric power generator, or so-called the thermoelectric module. And then we also can have the thermoelectrochemical cell. So usually this kind of thermoelectrochemical cell is based on liquid or not a solid state material. And it's based on the electrochemist fundamental to produce or to change the temperature difference into that electrical energy. And this kind of thermoelectric device, it have many advantages. For example, it's small, it's lightweight, it's long lifespan, and it's noiseless, because it don't need to have a very big surface. For example, like the solar cell, we need to collect all the sun rays intensity. But for the thermoelectric device, we only need the temperature difference. So it can be fabricated in the small size, and then it don't have any mechanical part, so that we can have a noiseless system, a quiet system, especially when we want to integrate with the window or the building component, because we cannot produce too much noise that we interrupt the resident inside the building. So if we see the power generation efficiency as a function of the source temperature in this picture, yes, there are many challenges still remaining in thermoelectric field. So here we can see the comparison between the most efficient cycle, which is the Carnot cycle, and the other conventional thermal energy produce electricity. For example, like the Rankine cycle based on the steam turbine, or the Brayton cycle based on the gas turbine. So we can see here that the current performance of the thermoelectric, so currently we are managed to increase until around 1 or 1, around 1 to 2. So it's still lower if we compare to the other type of production of electricity. So in this thermoelectric field, there are many tasks that need to be done in order to apply or to improve the performance of these thermoelectric devices. Especially if we want to use it as a power generation, instead we are using it as a power harvester. So if we look more detail about the thermoelectric device, usually when we want to characterize the material or the device itself, we usually use this figure of merit Z. So this figure of merit Z is proportional, exponentially proportional to the efficiency related to that conversion efficiency. So if we increase this figure of merit, we can increase the thermoelectric conversion efficiency. So this Z is equal to the material parameters, which is the S, the Seebeck coefficient, sigma is the electrical conductivity, and kappa is the thermal conductivity. So if we see in this graph, which show us the dimensionless figure of merit, ZT, multiply with the average temperature as a function of the year, so we can see that right now we can have in experimental level, we can have until 2.5 something. So I think this is based on until 2017 data. And the conventional one, we are using the telluride based material. So it's around 1 to 2 something dimensionless figure of merit. So we know that inside the thermoelectric field, one of the challenges is to find the best material and efficient thermoelectric material with ability or with good environmental or friendly environmental friendly. So we don't want, actually we don't want the toxic material inside our thermoelectric material. And if we look in detail about the figure of merit, we know that it's quite difficult to enhance or to improve the efficiency or the figure of merit, because we can see that this Seebeck coefficient, sigma, electrical conductivity, and thermal conductivity.
So you have muted, sir. Excuse me, sir, you have muted. Please unmute yourself, sir. Yes, sir.
Can you hear me?
Yes, sir, yes.
I'm sorry for the technical problem. Okay, sorry for the technical problem. So we go back about the figure of merit. So we know that these material parameters are strongly depend to each other. Then if we increase the Seebeck coefficient, we will decrease the electrical conductivity, and it also will affect the thermal conductivity. So usually, if we plot the relation between that Seebeck coefficient, electrical conductivity, and the thermal conductivity, we know that we need to find the optimum value to have a good thermoelectric material. And it is reported it lies inside the semiconductor material with a heavily doped or with high carrier concentration. So it's about around 10 to power of 19. And then if we look in this figure of merit, we can see the above part, this Seebeck coefficient power of 2 multiply with that electrical conductivity. We call it as the power factor or the thermoelectric power factor. And the bottom part, which is the thermal conductivity. So this graph shows the relation between the power output as a function of that thermoelectric power factor. So we can see here that we need to improve that thermoelectric power factor. And we can see, for example, this one, the half-use slur material can have high power factor and high power output intensity, power output density. And then if we see for the smart window application, we need to have, for example, like the electrochromic smart window, we need to have the output around few volt, and then the power around 0.2 watt per density. Okay. So it is important for us to improve this figure of merit and to improve this thermoelectric power factor. And in this study, we will focus on the thermoelectric power factor. So just I mentioned that if we want to integrate the thermoelectric device with that smart window, so we need to consider the environmental and cost consideration when we want to choose the material for applied to be the thermoelectric material. And then we need to enhance the thermoelectric conversion efficiency. And then we also need to have that multi-functionality of that material, especially if you want to use that for the multifunctional smart window. So in our research, we are trying to integrate this thermoelectric device with that self-powered smart window. So we have two approaches. One is we try to develop oxide material on glass substrate. So we want to produce thermoelectric material fabricated on glass because we know that the window is based on the glass. And then we also have the other approach where we try to develop a tinted film or the window film based on flexible organic thin film. So if you can see here, this is some example of the transparent organic thin film that we are currently research, and then it quite flexible. So you can see here that we bend the polymer thin film like this. Other than that also, we also focus on fabrication, thermoelectric characterization, and we also try to develop the thermoelectric characterization, especially for the thin film and also for the flexible material, and also all the other properties that related to that thermoelectric properties. Okay, so for today's topic, I would like to share with you all related to the oxide material on the glass substrate, focusing on the titanium dioxide, which is the TiO2. Okay, so if we look on the TiO2 to be applied as the smart window material, so we know that TiO2 is already used as the UV protection. So it's well known that it have been used as inorganic component inside sunscreen lotion, which act as a physical sunscreen by absorbing or reflecting and scattering the UV radiation. And it also have been reported that water repellent of the TiO2 material is good. It shows high hydrophobicity. So if you want to use the hydrophobic ability to repel the water on the surface of the window, so we can also consider this TiO2. And then it's also reported that TiO2 have a good visible light transparency. So if you can see here, this is some reported TiO2 material docked with niobium and B. So we can see it's have a quite good transparency. And we know that this oxide material is quite low cost, environmental friendly compared with the toxicity material like the telluride base, fabricable on the glass. We know that if we are using the solar cell and so on, so usually the TiO2 are fabricated on the FTO glass substrate. And then it's also integratable with other energy harvester device. Just I mentioned, it's also usually used inside the solar cell, especially the DSSC. And then just I mentioned, a material used in solar cell, and it's possible to apply this TiO2 as a good thermoelectric material for this smart window. So if we look on the thermoelectric properties of the TiO2, So this is some theoretical report regarding the rotile phase TiO2. And it is reported that the rotile phase have a higher figure of merit, the dimensionless figure of merit, compared to the other polymer. For example, like the brochite and also the anatase. And then we also can see from this figure, the ZT of the TiO2 is much depend on the temperature, and then TiO2 can operate until quite high temperature, 2100 Kelvin. So it's good for many kind of application. And then it also strongly depend on the carrier concentration. So this is in general in thermoelectric material, just I mentioned that it is strongly depend to each other material properties, the Seebeck coefficient, electrical conductivity and thermal conductivity, and also the carrier concentration. So if you see here that theoretically, it can be have the optimum value of that dimensionless figure of merit at the higher concentration of carriers, and it can achieve almost one of that dimensionless figure of merit. So it has high Seebeck coefficient already reported. Rotiles is around 0.36 until 0.7 millivolt per Kelvin, and it have quite low thermal conductivity, around 6. And if we look on the pure TiO2, the ZT is around 0.016 at this kind of temperature. So it's still low if we want to compare with the other conventional material. And then there are several approaches that have been done to increase the ZT of TiO2. For example, by doping, increase the numbers of carriers inside the TiO2. So we managed to increase the reported one, managed to increase the electrical conductivity. And then we can reduce the TiO2, which is the oxygen vacancy inside the TiO2 lattice. So we can decrease the thermal conductivity and also introduce the nanostructuring. It also can decrease the thermal conductivity by introducing the phonon scattering and also the grain boundary scattering to reduce the thermal conductivity. And currently, the highly reported ZT is reported at 0.35 at high temperature, around 973 Kelvin. So if we want to use this TiO2 material as a smart window material, yes, it has a potential, but it has many challenges, and one of it is to improve its thermoelectric properties, especially at room temperature. Because if you want to use for the smart window, it need to be used at much lower temperature, around 300 to 5 or 400 Kelvin. So if you want to use the window at much higher temperature application for some niche application, some niche space or some niche building, so we can have much better performance for that kind of application. Okay, so in our studies, in order to integrate this thermoelectric device with that self-powered smart window, so for this talk, I would like to share the first one about its self-cleaning ability. So the hydrophobic properties of the rotile phase TiO2 thin film, and then about the UV shielding ability. So I would like also to share some of the progress result about the percent UV transmission of that rotile phase TiO2 thin film, and then to evaluate the thermoelectric properties, which is we focusing on the thermoelectric power factor of rotile phase TiO2 thin film. So in this study, in order to improve the thermoelectric properties of that TiO2, so we are trying to introduce nanostructure inside the TiO2, and then we want to find what is the influence of nanostructure on the related properties, especially on the thermoelectric power factor, which is the Seebeck coefficient and also the electrical conductivity, and then try to clarify the influence of doping, because we know that the thermoelectric properties, the S, the stigma, and the kappa, is very strongly depend on the carrier concentration. So we would like also to clarify the influence of doping on the related properties and also to the structure of that nanostructured thin film. So what we do is we propose two kind of structure. One for the low temperature application where we fabricate on the FTO glass substrate by using hydrothermal method. And the other one is for the high temperature application where we fabricate or grow the TI2 layer on the quartz glass substrate. So this we are using the spray pyrolysis deposition technique in order to grow the TiO2 layer on the quartz glass substrate. Okay, so we have done the many characterization for the structural analysis, wetness analysis, optical properties, thermoelectric properties, and so on. So the first one for the hydrothermal method, where we managed to our collaborators managed to propose a technique to fabricate the two kind of layer. One is the B layer, consists of the nano rod and nano flower, and one is the single layer, consists only nano rod structure of that TiO2. So by using the hydrothermal method at low temperature, the synthesized TiO2 layer is observed to be rutile with this respective peak at 110, 101, and 111. And we also can observe that the dense TiO2 nanorod are in square shape, and the B layer, we have two layers, the nanorod and also nanoflower also can be fabricated. And then this TiO2 layer is also observed uniformly deposited on this FTO glass substrate. And if we are using the spray pyrolysis deposition technique, so we can see that after we anneal at high temperature, because by using this method, we need to anneal to high temperature to obtain the rutile phase. So we can see here when we anneal it until 800, 900, 10,000 degrees. So we can see that that TiO2 layer become a rutile phase TiO2, but we also can see that when we increase the temperature, we also can observe the porosity inside the TiO2 layer. So for the first one, the ability of to repel the water for that smart window. So we are using that hydrophobic surface in order to collect all the contaminant particle in front of the window and to remove it from the rough surface through the rolling droplet. So if we plot the contact angle measurement, compare with the material, so we compare with the quartz, we compare the FTO, and then we compare with the porous TiO2 layer, which was fabricated by using the spray pyrolysis deposition technique. And also the nanorod, the B layer contain nanorod and nanoflower and single layer nanorod only. So we can see that we can improve the hydrophobicity of that TiO2 layer. And we can see here that the nanorod layer, the single layer, have the highest hydrophobicity or the contact angle near to the super hydrophobic ability. So this is likely due to the layer roughness and high aspect ratio of that TiO2 nanorod. And then if we see from the ability to repel the UV light or to block the UV light, so we also have done a measurement on the UVA and UVB range, around 320 to 400 nanometer for UVA and 280 to 320 nanometer. So we know that this UVA and UVB can affect the biological body, especially UVB and UVA can come into the deep inside our skin surface. So if you see here, we have calculated the percent UV transmission. So it's reported that if we have less than 2.5% UV transmission, we can have a 3 grade, which is classified as an excellent protection. So if we plot the graph or the percent of UV transmission as a function of that sample, so we know that all the rutile TiO2 layer have an excellent repelling, have an excellent blocking UV ability. So this synthesized result These results show the excellent UVA and UVB protection, and we know that it's not governed by the layer structure. So when we check with the absorbance, so we expect that, or we assume that this excellent in the blocking ability is likely due to the absorbance of that TiO2 material itself. Okay, next we look on the thermoelectric power factor. So this graph shows us the thermoelectric power factor as a function of the temperature. So we have measured two types of material. So just I mentioned, we have B layer, which consists nanorod and nanoflower. So we use this NRD and NFST. And one more, this square shape, only single layer, which consists only nanorod structure. And then we also have varies the thickness. For example, this nanorod around 4 micrometer, we reduce until around 2 micrometer. For B layer, we have 10 micrometer and 8 micrometer. We also plot inside this graph with the bulk TiO2 represented by this triangle, and we also have plotted the reported aluminium dot zinc oxide by this diamond. So we can see here that the thermoelectric power factor is influenced by the structure of the TiO2 layer. So we can see here that the B layer have higher thermoelectric power factor compared to the single layer that consists only nanorod layer. And then if we see from the thickness, the 4 and 2 micrometer and 10 to 8 micrometer, so we cannot observe a significant influence of the thickness on the thermoelectric power factor. Okay, so we can observe from this graph. So the thermoelectric power factor of this TiO2 thin film is depend on the structure, where the B layer have the high thermoelectric power factor compared to the single layer, which consists only nanorod, and it's not depend on the thickness of that TiO2 layer. And if we compare with the bulk TiO2, we can see that the thermoelectric power factor of that nanostructured thin film are smaller than that bulk TiO2. So why this happened? There are many possible reasons that we can think about it. The first one right now is the difference of the structure. So we know that the Seebeck coefficient, for example, we can have two components. One component is the electronic contribution of the Seebeck coefficient, and one component is the phonon drag contribution of that Seebeck coefficient. So if we compare with the other semiconductor material, for example, like the silicon, usually at either at higher temperature, at the room temperature also, we can see that this phonon drag observed inside or in bulk silicon. So we can consider that this difference between the bulk TiO2 and that nanostructure TiO2 is due to the elimination or the demolition of the phonon contribution or phonon drag contribution inside that Seebeck coefficient, because we have quite a nanostructure inside the TiO2, because in, for example, like in the silicon, even though it's in microstructure, it also can be observed the reduction inside the Seebeck coefficient due to that elimination of the phonon drag contribution. And if we relate this also with the thickness, we also know that the thickness is still not influence this phonon drag contribution if we have this kind of thickness around micrometer. So that's why we can see here that the thickness is not much influence the thermoelectric power factor of this nanostructured TiO2 thin film. And then if we look on the temperature itself, so we can see here that the thermoelectric power factor of that nanostructured TiO2 is weakly depending on the temperature until around 380 Kelvin. However, above that, we can see a little bit dependency on the temperature. Comparing with the bulk TiO2, we can see that is very depend on the temperature. So we can also say that we can have a stable thermoelectric power factor in this temperature range, around 380 Kelvin, something like that. Okay, so if we compare with that reported aluminium dot zinc oxide, we can see that our B layer uh, uh, are much larger than that thermoelectric power factor of that aluminium dot zinc oxide. So if we see here that we are still not using doping or introduce doping inside that nanostructure TiO2, so we can expect more possible increase inside the thermal power factor by using the doping. Okay. However, if we compare with the conventional material like the telluride-based material, it's still very far, still low. So there are still more challenge that we want to improve this thermoelectric power factor. And then, since I already mentioned that there is a possible increase inside the power factor by doping, and we also know that these thermoelectric parameters is strongly depend on the carrier concentration. And next, we want to clarify what is the influence of doping on this nanostructured TiO2 thin film, especially on the thermoelectric power factor and also the nanostructure itself. Why? Because if we cannot preserve or we cannot keep the structure of the nanostructure, so we can lose the benefit to reduce the thermal conductivity, because we know that when we introduce nanostructure inside a material, we can increase the phonon scattering, boundary scattering, and so on to reduce the thermal conductivity. So what we do is we dope the nanostructured TiO2 thin film with silver or Ag. So we're still using the hydrothermal method, and then we change the composition or the weight percentage of this Ag and O3, the argentum nitride inside the fabrication process. So when we increase the weight percentage or the amount of doping 0.1, 0.25 until 0.4 Kelvin, and we observe from the FESAM image, this above is the nanorod, the single layer, and the below one, 1, 2, 3, 4 is the B layer, which consists the nanorod and nanoflower. This one is for the undoped. This second row is for 0.1 gram. This is for 0.25, and this is for 0.4 gram. So if we see here that we can observe the fabricated film still consists the dense TiO2 nanorod in square shape and B layer of nanorod and nanoflower. So you can see nanorod single layer, and also B layer consists nanorod and nanoflower. We also can observe when we dope, we also can observe the TiO2 still uniformly deposited on the FTO layer. And then we also can observe that this TiO2 layer structure, either is a single layer or B layer, are likely not affected by that addition or the doping of that Ag and O3 either until 0.4 gram. So if we looking on the XRD and also the EDX result. So for example, this graph shows us the SRD result for the DOP B layer, DOP single layer, and undoped B layer and undoped single layer. So we can see that the synthesized DOP TiO2 layer still observed to be rutile with the respective peak at 110, 101, and 111. However, if we see carefully inside this SRD, we can see a little bit shifted of the peak at the higher degree. So this is considered due to the different size of that nucleation atom of the argentum, ionic argentum, ion argentum, and ion titanium inside the structure. So this will affect the lattice parameter that we shift this peak of 110, 101, and 111. And if we see from the EDX result mapping, together with the mapping of TI, O, and E, sorry,
Please participants mute yourself. M already. So please mute yourself.
sorry for the technical. Okay, so if we look from the EDX result, we can see that it's quite difficult to find the peak of again the silver at around 0.8 kilo electron volt. This is for undoped. This is for the doped. Sorry, well, both is for the doped at 0.4 gram. So this is for the B layer, and this is for the single layer. So if we look on the mapping itself, so we can see the, I'm sorry, the picture is not very clear. So the TI and O we can see is uniformly distributed inside the mapping. Actually, we can also see, hardly observe the distribution of argentum. Why? Because it's quite low, the weightage percentage that we put inside the chemical when we put the AgNO3 inside the process. So it's below 1%. So it's quite low. So that's why we consider that it's quite difficult to see the mapping of argentum or the silver inside this mapping, elemental mapping. So we can conclude that from this XRD and EDX result, the synthesized TiO2 layer is observed to be fertile. Silver element is not detected, and we can also consider that the silver is homogeneously doped into that TiO2 rutile structure. So if we plot the thermoelectric power factor as a function of the amount of doping, so we have three kind amount of doping. So this green square shape show the B layer, which consists the nanorod and nanoflower, and the circle one shows the single layer, which consists the nanorod, and the diamond shows that the bulk TiO2. So these are measured at room temperature. So we just measured at one temperature, and we can see here that the nanorod, nanoflower, which is the B layer, can be improved by using doping. So we can see here it is improved around 3 times larger compared with the undoped. I did not put the magnified graph. Actually, if we magnify this part, the nanorod also increase a little bit compared with the undoped. So here we can see that by doping, we can improve the thermoelectric power factor of the B layer, which is larger than the bulk TiO2 and also larger than the nanorod. So what we consider is through doping, we can increase the carrier concentration. So we have also measured the carrier concentration by using the Hall effect measurement. So we can see that by increasing the amount of doping, so the carrier concentration inside that B layer and single layer structure are also increased. So when we introduce silver or argentum inside the TiO2 lattice structure, we expect that it will increase the oxygen vacancy in the surface, that will introduce more carrier concentration carriers inside the TiO2 layer. So if we see here, the increase inside the thermoelectric power factor of this both thin film, so it's much depend or governed by the electrical conductivity. So this graph shows us the electrical conductivity, the red color, and the left y-axis is the Seebeck coefficient as a function of that doping amount. So we can see here that when we increase the doping amount, we can increase the electrical conductivity. So for the B layer is almost 4 times larger, and for the nano road is almost 2 times larger. However, if we see the seedbed coefficient, there is slightly decreased, but we can say it's almost look like constant, but have a slight decrease. Okay, so we can see here that the increase in the power factor is mainly governed by the electrical conductivity, and the improvement of the electrical conductivity is due to the introduction of or the increase in the carrier concentration by that oxygen vacancy when we dock with that silver. Okay, so we can consider the increase in electrical conductivity contributes to the enhancement in the power factor of TiO2 thin film with dock as low as 0.4 gram of argentine nitride inside the process. And we can see that the structure also not much influenced by the doping. So we can keep the benefit of the nanostructure. Simultaneously, we also can increase the thermoelectric power factor by increasing the carrier concentration. So I believe the time is up. So lastly, I would like to conclude my sharing. So we have successfully synthesized the rutile phase TiO2 thin film on glass substrate. And then we have shown the hydrophobic ability of that two kind of layer, bilayer and single layer. And then we also have shown the ability to UV protection. And then we also have shown the power factor, the influence of nanostructure on the power factor of the TiO2 thin film. And we also have shown the doping influence on the thermoelectric power factor of the TiO2 thin film. So that's all my sharing. So I believe the time is also up, isn't it? I think 10 minutes is for the question and answer.
Yeah, thank you, sir. Thank you so much. You were given wonderful talk, sir. You were explained clearly the synthesis of nano-structured retail-based titanium dioxide with the age doped and how the fabricated nanostructure improve the thermoelectric conversion efficiency of thermoelectric material and decrease in thermal conductivity. So, and also the further dopant, how enhance the thermal electric conversion efficiency and all. So, a very nice presentation, sir. This is well received by the participants. Thank you so much, sir.
Thank you very much.
Yeah, dear participants, so if you have any queries, so please ask now. So please unmute it yourself one by one. So please ask.
Hello, sir. Did you check what about the figure of merit of your titanium TiO2 coated AG coated?
I'm sorry.
Hello. Hello, sir.
Yes.
Yes, sir. What about the figure of merit, sir?
The figure of merit, we did not evaluated it because we still short data of the thermal conductivity, because we only have the thermal conductivity right now only for the nano road. I hope that in near future we can provide you the figure of merit. So right now we only have the data for the thermoelectric power factor.
Okay, sir. You tried only TiO2, or we have so many thermoelectric materials like bismuth-telluride, bismuth-selenide, and zinc ceramides, so many things available now. So you tried only TiO2 or some other material also, sir?
In our research, we are focusing on two types of material. The oxide material, we are only focusing on the TiO2, and one more we are focusing also on the organic material, which is based on the polymer.
Okay, sir. Thank you. Thank you, sir.
Okay, welcome.
Natar sir, there is one question in chat.
Yeah. Sir, one more question from the participants, Sudhaji. Sir, why P-type thermoelectric material shows higher ZT than N-type materials?
If I'm correct, either the P-type is higher than N-type material. Am I correct?
Yes.
This depends on the material itself. Not really the P-type is much higher than N-type, so it depends on the material. Sometimes maybe the N-type is higher than the P-type. So because it's depending on the material, either the whole or the compound inside the material. So it's quite difficult if you want to say that the P-type is higher than the N-type. So it depends on the material.
Yes, sir. Yes. Yeah, thank you, sir. One more question from the Neha Prakash. High porosity and rough layer usually results in increased catalytic activity. As for the thin film mentioned, will the roughness not increase the impurity contamination on the surface, sir?
So I believe that when we said about the attraction on the surface by reducing the energy of the Pi, so for example, inside the doping, we also expect that the silver will interact with the surface of the Pi and will deposit or form the metallic agentum on the surface of that PiO2. So that is also a possible reason why the increase inside the electrical conductivity. But further work needed to clarify that things because we still don't have the theoretical calculation to prove that. We just consider that as one of the possible reasons why of that thermal conductivity can also influence the thermoelectric properties of that PiO2.
Yes, sir. Sir, one more question from the Celestina. Which nanostructure will give more ZT value, nano rods or nano flowers?
From based on our result, we have that the nanorod nanopower, the B layer, have the higher thermoelectric power factor. So this is likely due to the more smaller elimination of the phonon drag contribution inside the seabed coefficient. However, if we consider about the figure of merit, there are some sort of take and give over there because we assume that the single layer, we will have more reduction inside the thermal conductivity compared to the B layer. However, we still not enough data to prove that. So it's still quite difficult how much it will decrease the thermal conductivity compared to the B layer and single layer. What we still believe that the B layer can be much higher than only the single layer because I think the reduction in the thermal conductivity, for example, in the single layer, that we can reduce around 3 times. And I believe that for the B layer is almost around like that for 2 times or 1 times. So compare with the increment in the thermoelectric power factor, which is around 4 times combined with the doping.
Sir, what substrate material suitable for high temperature thermoelectric application? Glass or any other materials?
It depends on our application. For example, right now we want to use for transparent application. So if you use the glass based on the FPO and so on, so it cannot stand for the high temperature. That's why we also fabricate on quartz because we know that the quartz can stand much higher temperature. So it depends on what your application. So if you want to use a for transparent application, so you need to find a transparent material like the glass or the quartz. So if you want to use the specific application, so you can you don't have requirement for transparency. So maybe you can choose or you can select a much higher temperature withstand temperature of material. But for right now, for this kind of application, for high temperature, we use quartz, and for the low temperature, we use the glass for that.
Thank you, sir. Thank you very much for your informative speech. Thank you very much, sir.
Thank you, sir.
Very much
Thank you.
again.
Thank you so much, sir. Very interesting, inspiring speech.
Thank you very much again for inviting me and for give these wonderful opportunities for me to share my research work, our research work. Thank you very much again, the Department of Physics, and thank you very much to all professors and the chairman.
Thank you, sir. Thank you. So we'll move on to the next session. We'll move on to the plenary talk of Dr. Nobuo Saito, Professor, Deputy Director, Analysis and Instrumentation Center, Nagoya University of Technology, Japan. Now I request Dr. Sanjurani ma'am, Assistant Professor, Department of Physics, to introduce our speaker, Dr. Nobuo Saito. Sanjurani ma'am.
Yes, thank you, Dr. Beena, and very good morning to all of you. I am very happy to introduce Dr. Nobuo Saito, Department of Material Science Technology, Analysis and Instrumentation Center, Nagoya University of Technology, Japan. He earned his degree in PhD in engineering from Nagoya University of Technology in the year of 1999 and joined the Analysis and Instrumentation Center, Nagoya University of Technology, Japan at the same year as assistant professor. In 2006, he has promoted to associate professor, and in the year of 2019, he has become a sub-director of Analysis and Instrumentation Center at the Nagoya University of Technology, Japan. He is having number of papers in his field. He is a member of the Chemical Society of Japan, Catalysis Society of Japan, and the Surface Science of Japan. Along with this, he is also a member of the Japan Institute of Metal and Materials. In today's session, Professor Saito and his team is going to give the live demo how we can use the XPS and TM in a remote control condition. Professor Saito, on behalf of SRM Institute of Science and Technology, Ramapuram campus, now I welcome you to deliver your talk and show us a demo. Dr. Saito?
Yes. Thank you for introducing me. Nice to meet you. I'm Nobuo Saito, Associate Professor of Nagaoka University of Japan, Nagaoka University of Technology in Japan. Today, I'd like to do the demonstration of remote controllable analytical equipment. Especially today, I'll show you a TEM and XPS remote control. So, first of all, I'd like to say thanks to the SRM staff. It is an honor to be able to attend this conference. Thank you very much. So, first of all, I'd like to introduce myself. My name is Nobuo Saito. My particular field is catalyst chemistry and surface science. And especially, I'm good at operate analytical equipment. And I have a laboratory. The name is a Photo Energy Conversion Material Laboratory. In my backbone is a catalyst chemistry. Especially now, I'm interested in photocatalyst for overall water splitting. But today, I didn't talk about my research field. Today, I'd like to talk remote controllable equipment. And I'm sorry, just a moment. This is my family and my lovely dog. Okay. This slide shows the outline of this my presentation. My presentation is divided to two parts. Part one is the introduction. introduction of our university. Our university name is Nagaoka University of Technology. We call it NUT. The second is introduction of Analysis and Instrumentation Center. We call AIC. And installed remote controllable analytical equipment. And our university do the share project. The share project, the subtitle is GIGAKU. GIGAKU is a Japanese word, Innovation Network for Equipment Sharing. So it is difficult to explain GIGAKU in English, but this kanji, Japanese word, gi is a technology, gaku is a study. So most researchers think important thing is the science, but in our university, most important thing is technology. First is technology, second is science. This is our university strategy. Finally, if there are time, I'd like to introduce our center by using this smart glass. So second part 2 is a demonstration. So the equipment is FETEM, JEM 2100F. The second is the XPS. This XPS recent type apparatus. The maker is Thermo Fisher Nexa. Okay. Okay. First, I'd like to introduce my university. You can see here the bird eye photo of Nagaoka University of Technology.
Dr.
Our
Saito,
university.
Dr. Saito, you are not sharing your slides.
Okay, sorry. I'm sorry. Yes. Can you see?
Yes, yes.
I'm sorry.
Yeah.
Only my face. I'm sorry. So, you can see here bird type photo of Nagaoka University of Technology. Our university is located. Our university is located of center of Japan. So from Tokyo, it takes about 1 hour 14 minutes by using Shinkansen. Shinkansen means a new track line. The number of undergraduate and graduate students approximately 1,000. And also 1,000. Total is approximately 2,000. Very small university. If you look at our campus map, our campus picture, you can see the campus is covered with a lot of snow in the winter. This shows the department of our university. There are mechanical, electrical, information, material, and civil and bioengineering. With regard to doctor program, we have 1, 2, 3, 4, 5 course, doctor course as shown. Okay, next, I'd like to introduce our analysis and instrumentation center. Our center equipped with 60 type of large-scale facility and analytical equipment. So there are many equipment. If you want more in detail, please access to our URL, Nagaoka University of Technology. In our center, no operator exists. Operator is a student. If student want to use our equipment, first student visit our center, and staff and student discuss about purpose of analysis, and we do the private training to the student one to one, by center staff. So most important thing is no operator and student is operator. And next is a share project at Nagaoka University of Technology. So I mentioned Gingaku is important of our university. So this share project started in 2019 with the support of the Open Advanced Research Facility Initiative by the Ministry of Education, Culture, Sports, Science, and Technology, MEXT in Japan. This is a share logo. And in a domestic area of Japan, this network is north is Hokkaido, south is Kagoshima. So very wide area network. Okay. Next, I'd like to introduce how to remote control of analytical equipment. We divided to the two types. One is a semi-remote control. This means a collaborative measurement by using real-time monitor sharing system. Here in after, we refer to the semi-remote control. Please, I'm sorry, this is the Japanese. So the other is we call a full remote control. This means a direct operation from remote location with exception of sample installation. So the full remote control. So here you can see how to connect to how to connect to network in case of semi-remote control and full remote control. I'm sorry, but this is Japanese. So here you can see analytical equipment. This is a scanning electron microscope. So system is very easy. Semi-control means a monitor sharing system. So this PC is a control PC of equipment. So this signal shows a monitor signal. So monitor signal is divided to two lines. One is a monitor PC. The other is the other go to the capture unit, and the capture unit connect to the PC, and this PC shows a monitor, screen monitor, and we can observe same image in this monitor. And this is a internet line. So this PC is a remote control PC, yeah, normal PC. This PC and this intermediate PC is connected connected. And by using TV meeting system, for example, such as Teams or Zoom or Cisco WebEx, and we can see a monitor and discuss with analytical condition. This is a semi-control system. So the other is a full remote control. Here you can see XPS, and this is also same. In this case, we set intermediate PC. So because it is dangerous that direct connection to the equipment PC. So we set intermediate PC and network divide two area. One is local area, the other is worldwide area. So in this system, this intermediate PC control this equipment PC by using P2P, peer-to-peer remote control software, such as this is a software name, Laplink or NetOp. And this PC controls this PC. And inside this side means a World Wide Web connection. So by using remote, Team or Zoom TV meeting system, this remote PC control this intermediate PC by using a remote desktop function of TV meeting system. So after my introduction, you can see this system, this demonstration. The other is a VPN network connection. So if we use this system to the company keep high security. So in this case, we set a VPN router in both sides. So this system is have a high security. Okay. So remote control. Next is what kind of PC? What kind of remote controllable analytical equipment we have? You can see the URL, but in our university. This is our university homepage, but I'm sorry, this is the Japanese version. So you can find share project logo. Please click here. You can see many types of remote controllable equipment. Just a moment, please. I'm sorry, this is Japanese, so. So you can see many types of remote controllable equipment. So this is a SEM, EPMA, DDoES, XPS, FEOJ, laser Raman spectroscopy, XRD, and ESR, and high type, this is also XRD and XRF, FESM, EDS, EBSD, and this is a TEM. The maximum acceleration voltage is 120, and FID and desktop type SEM, and cryo type SEM, desktop SEM, micro focus X-ray CT, and there are many analytical remote controllable analytical equipment. Now, you can see real-time analytical, remote controllable analytical equipment. So, you can see here, just a moment, please. Where is the XPS? So the where is 10? It's difficult to find. I'm sorry. I'll explain later. Please see a demonstration. Okay. So next is a demonstration, but prior to demonstration, I'd like to introduce my analysis and instrumentation center by using this smart glass. Please wait. Can you hear me? Dr. Sanjurani, can you
Yes.
hear me?
Yes, I can hear you.
Okay. Okay.
Yes, we can see the corridor.
So this is a analysis idle of our analysis and instrumentation center.
Yes.
I go to entrance of analysis. Okay, now I use a Wi-Fi system. So, but sometimes I think signal low, so it is difficult to hear. Okay, can you hear me?
Yes, we can hear you and we can see also.
Okay. So I have to use this.
Sanitizer.
Okay. So this is our center. You can see many equipment. So this is my center office. So this is a reservation system. This is the reservation system, and many you can see a movie of all room. And this is EPMA, but this is very old one.
Okay.
Okay, can you hear me?
Yes, we can hear you.
No sound?
No,
Okay.
your voice is clear.
Just a
Yes.
moment.
Yeah.
And so I'd like to introduce remote controllable system. So this this equipment, in this equipment, control system is Unix, not Windows. So we use this remote control system. This is a KVM system. So we connect this cable to the mouse and keyboard, and we control this keyboard and mouse. And the monitor signal is here. So we can control this unit from this computer.
So, Dr.
So this is
Saito, this
yeah.
PKMS is also remote control. Means we can use, is it semi remote control or full remote control? Dr. Saito?
Yes.
Yes,
I'm sorry. So I got the idea. Okay.
Okay.
Okay. So this is FEOJ and XPS. You can see a remote control system.
Okay.
Okay. As I mentioned now type of remote many type of remote control equipment. So next is a demonstration. So you can see many analytical equipment, remote controllable equipment. This is a radar Raman spectroscopy. So all equipment equipped with this computer, and this computer can remote control this machine. Okay, please wait. Okay. So let's go to the part 2 demonstration of analytical equipment. So first is chem remote control. We call semi-remote control. So I use Japanese, sorry. 手持ち OK ですか?
OK です。
Dr. Seamus, please start demonstration.
OK。
Please.
じゃあこれでシェア、図面出してもらえますかね。
はい。
Hello, can you hear me?
Yes, yes, we can hear. Yes.
Good afternoon and good morning, everybody. And I'm glad to here to share our research equipment with you. And I'm Suemasu at Nagoya University of Technology, and my major is high TC superconductivity and oxynitride hard coatings, and also nanosized particle production by using plasma. So today I'm going to talk about, explain about our transmission electron microscope. And we have a field emission gun and 200 kV electron microscope equipped with EDS and also an EOS. So let me introduce our research capability using chromium nitride nanosized particle doped with many cations. Okay, so this is an EDS. Can you see the EDS spectrum? I think I'm sharing an EDS spectrum with you.
Yes,
okay, good. And so this is an EDS spectrum obtained a few minutes ago from a small grain with a diameter of 10 nanometer. And you may see peaks of cations, vanadium, titanium, and also niobium, zirconium. So they are dopants, and also chromium and titanium L lines. But those L lines are overlapping to the oxygen Kp and also nitrogen K peaks. So that we don't know oxygen and nitrogen is inside of the sample or not. So our research capability includes the EOS, so that we do the EOS analysis. じゃあこちらにしていただけますかね。So this is a live image of a transmission microscope. You may see on the left-hand side, and so this is a high magnification lattice image. You may see a lattice image around here. And a few minutes ago, I have recorded the image in here and enlarged. And I measured the lattice interplanar distance, which is 2.31 nanometer for 10 lattice. It means 2.31 angstrom for each interplanar distance. And those are comparable to interplanar distance planes have a 90-degree angle. So it means that there's a cubic 200 planes. So it is what we expect from chromium nitride. And chromium nitride is an NaCl structure, and vanadium and titanium and also zirconium niobium are doped from the EDS. But we are not sure that oxygen nitrogen. And so what I did was an EOS analysis, and this is the EOS spectrum. And when we zoom in the EOS spectrum, so that you may see heavy elements, titanium and vanadium and chromium, and along with the oxygen small peak and the nitrogen edges. So it means we intend to make a nitride, but a small amount of oxygen is also involved. So actually what we found was that oxygen doping can enhance the hardness by 60%. So it is favorable for the hardness increase of this material. So actually what I showed today was what I exactly did a few months ago with my collaborator in Hokkaido, which is 1,000 kilometers apart from Nagaoka. So basically that the distance is not a big difference, so that I'm willing to collaborate with you guys in India as well. So thank you very much for your attention. 斉藤先生、お返しします。
Thank you.
Thank you, Professor
Accept.
Sematsu. So next is a full remote XPS measurement. So XPS room, are you ready? XPS room, Fuku-san,
Hi.
are you ready?
Hi. Can you hear me?
Yes, we can.
Okay.
Hi.
Okay, please start demonstration.
Hi. So thank you. Good afternoon, everyone. I am Tai Van Phước, and this is Dr. Ueno Sang. So we are as
Dr.
technical
Thai,
assistant.
Dr. Thai, sorry to interrupt you, but your voice is not loud enough to listen.
Okay. So can you hear me
Yeah.
clearly?
Yes.
Okay.
Yes. Yeah. Thank you.
Okay. So today it's my pleasure. We are pleasure to be here and present to you how to operate an SPS device by remote control. So now we are going to share our screen. Lovely. So can you see the screen?
Yes.
So let me a few minutes to introduce about this program, and then I will introduce you how to operate. So we can see here this screen of program Thermo Advanced to control an SPS called NESA. So in here, okay. So here is the photo of sample. You see the is where is holder and plug. How to say this plug piece is silicon wafer. You see here is the real view, and this is the mapping figure. And here we can see this experiment tree. So we can set up and control every parameter to observe SPS. So now I want to show you how to select position to observe. Okay. So first of all, I double click here. So you can see the cloud crest will move to the new positions. And a real and here is a real hi. Now I'm going to set up an observation. First one, we should use source. So we can see here many options. For example, real. It's the ion spectroscopy, UV photoelectron, and X-ray gun. Then we observe one point. So we select point. Sorry. One point. Here we can change the name. This. And then we want to observe the X-ray, so we select here and we select multi-spectrum. Now we can see the many elements that we can select and observe. So for example, because our symbol is silicon, so I would like to check silicon, carbon, oxygen, and I want to know the full scanning. So I select here and it's okay. So you can see this is four options to observe. This is for full screen, silicon, carbon, oxygen, and after that we should set up the run. So this is all operation that we should do to observe this. So in the morning, I already observed one point. This is here, not test one, and we can see the result right here. This first one is the result for full scanning. from 0 to around 1350 eV. This is for silicon, for carbon, and for oxygen. So maybe this is very easy to upgrade. So now we are today will observe with Dr. Sanjurani.
Yes, Dr. Thai.
Hi, so Dr. Sanjurani, I'm going to give you the permission to operate by remote control.
Yes, okay.
Okay, give me a moment.
Okay, dear participants, you can observe that here the Dr. Thai is going to give the remote control permission to me. He is in Japan and I am sitting in India. I can run my sample. So please see carefully your screen.
Okay, so now I already gave you the permission. So
Yes.
please show me your mouse moving.
Yes, participant, you can see there is two marker on the screen. One is white and one is black. So means
Okay.
the two person can run this system now.
Okay, so please move your mouse
Yes,
in the black sample.
in black center.
Hi.
This point you want me to select the area. Is it, Dr. Thai?
Hello.
Please, yes, please guide me what to do.
Please move your mouse.
Yes, I'm
Okay.
moving. Yes,
Okay. It's okay. Now please select one point in the black area.
on the silicon.
Yeah.
Yes,
Okay. One point.
yes, yes.
Double click in this.
Okay.
Okay. Double click. Now you see the live screen moving.
Yes.
Okay. Now in the left side, please select the run saw.
What? Can you repeat, plus?
Okay, this one,
Please.
the saw. The right. Okay, a little bit on right.
Yes.
Right on the right side. Just
This.
this one.
Yeah.
Click.
Source. Yes.
Yeah, source.
Yeah.
Click this
Okay.
and select X-ray
X.
gun.
Yes. I can
X-ray gun.
select. Yes.
Okay. Now we are going to observe one point. So please select point.
Plus.
Yeah, point.
Okay.
Select point.
Yes.
Okay. You can change the name. Look like double click.
Hmm. I can.
Okay, again. Click one time. Okay, you can
Yes.
change. Look
Yes.
like sunny point.
Test one. I want to give test one.
Okay.
Yes. Yes. I have given the name the test one.
Okay. In the below, please select enable auto height.
Enable
Yeah.
auto
Enable
heat. Auto heat.
auto
Oh, okay.
auto height.
Okay. Yes.
Now auto height.
Auto height.
Yes. And unselect auto analyze.
Yes. I have selected.
Unselect.
Unselect.
Yes. And select apply in the bottom.
Apply.
Under
Okay.
bottom.
Yeah. Read more. Apply. Yes.
Okay.
I apply.
Already?
Yes.
So now we select the spectrum. Going
Okay.
to the up. Okay.
Spectrum.
Select, okay, spectrum and multi-spectrum. Please.
Multi-spectrum.
Hi. So because our symbol is silicon, so we want to know about silicon, oxygen, carbon, and select survey spectrum in the below
Scan.
and left
Huh.
side. No. Survey spectrum. Insert.
Service
Okay.
spectrum.
Yeah,
Yes.
this one. And okay.
Insert. Yes.
Select again, please.
Yeah.
And okay. So we can see they have many options on the experiment tree. So
Yes.
in each spectrum, they have many, the number scan is too much, but today we want to a short demonstration, so please
Yes.
select only 2 times,
Mhm.
two
Yes.
times for all spectrum,
For
for
two.
carbon, carbon
Two I
2.
have checked.
Okay, apply, please. For carbon also.
Carbon.
Okay, carbon.
Yes, I have applied already.
Select carbon also, please. Carbon.
Where?
Carbon spectrum. Okay, and select 2 times for scan.
Scan.
Please change the number of scan from 50 to 2. 2. Okay. And for silicon also.
Oh, okay. So separately for all I have to select.
Yes, yes.
Okay.
2.
And
Silicon.
2
Okay, for silicon.
for silicon. 2.
2.
Okay.
Apply, please. Okay, now well done. We are finished to prepare. Now we are going to analyze process. So please select run. This is look like how to say. This is green button on the
Run.
yes. And
Where
the
I
right
can.
side, right side, please.
Oh, this one. Run.
Yeah, this one.
Okay. Shall I hit the run?
Yes. So now process is going to turn on the source of its ray. You can see the below that the signal change to float, and float gun is running.
Yes, you can see here float. Dear participant, you can see that now sample is running. Float
Okay.
is blinking.
Okay. So it took about 1 minute to one of the source is ray.
Yes. Now participants, you can see that the spectrometer. Dr. Thai?
Okay. Now
Yeah.
process is going to adjust the height of analysis chamber with sample.
Fuku-san, please explain now condition.
Height.
Waiting
Now,
time?
yes. Now process analysis is going.
Okay.
So we can see the screen is full scan from 0 to 100, 1300 EV. So the process will repeat 2 times as we said. Now process is going to scan for silicon peaks.
Dr. Sanjurani, my presentation time is over. Okay? Is it okay?
Yes, it is okay.
Okay. Please continue.
Yeah.
And for carbon peaks.
Now, Dr. Sanjurani controlled the XPS directly. And
Yes.
now I have to wait for several times. So I'd like to finish demonstration, okay?
Okay.
So after getting this data, you can analyze this data by remote control. But today, no time, so I'd like to finish, okay?
Yes, it is fine.
Okay, thank you, Dr. Sanjurani, to control remote control.
Thank you, sir.
Fuku-san,
Hi.
Ueno-san, thank you.
Hi. Thank you very much, Sanju Rani-san.
Doctor.
Dr. Sanju-san. Hi.
Thank you, Dr. Thai, for showing us this great demo.
Okay, I'd like to finish my presentation and demonstration. Thank you for your kind attention.
Thank you, Dr. Saito. It's very nice to see this demo, but means now I would like to invite question from the audience. And the first question is from my side, Dr. Saito. Is it possible in this pandemic situation, is it possible that a student can take the training in online fashion?
Yes, student can accept do the training by remote control, and student can use our equipment. And I'd like to make a strong connection between SRM and our university by using these remote controllable equipment.
Oh, okay. So is it possible that student in India, you will give the online training to student, and after that they can run the samples?
I have to ask our president.
Oh, okay.
But maybe okay. It is possible to make collaboration research between my laboratory and Dr. Sanju laboratory.
Yeah, okay. Okay, and means that you were showing the so many instruments like XRD, PPMS, all those are systems are in remote control. We can use in a remote control fashion. The other instruments also.
Other instruments. So today I'd like to introduce XPS and TEM, but we have many equipment. So other equipment is of course okay.
Oh, okay. Okay. So thank you.
But the training is important.
Oh, okay. Okay. So now participant, I would like you people to ask question if you are having, and please interact with Dr. Saito. Participants.
Hello, sir.
Yes. Yes, you may ask your question, sir. You are audible.
Hello, sir. This is Jagadish.
Jagdish.
Sir, am I audible right now?
Yes, yes. Now, Jagdish, you are audible. Yes, you may ask your question.
Hello, sir. Sir, through which platform we can access your instrument directly?
Excuse me, it is difficult to catch your question.
It's your voice.
Through which software we can access your remotely to your software, sir?
You connected our system directly?
Yes.
By installing some other softwares like some other platforms, or we have to use some your licensed products, sir?
I'm sorry, I didn't catch. So, Mr. Fuku-san,
Hi.
Can you understand?
He asked about which software that we use for
I'm sorry, which software? So, I use a remote control software, name is Laplink or NetOp. So, Windows remote control system is not good. So, because of sometime trouble occur.
Okay, sir. Is it free of access, sir? We have to pay for that.
Please
softwares are paid softwares. Remote controller softwares are paid. Is it your software is paid or free of cost, sir?
This is free or not free software, sensei?
Fuku-san, please.
This one is free or not free software that we should pay money to use.
So sorry, not free. I have to buy.
Okay, sir. So that after training we can access your softwares from India only, sir.
So, of course, we use the software, but remote control is only this Zoom system. So you can control our equipment.
Okay, sir. Thank you for a valuable demonstration, sir.
Hi, thank you very much.
Participants, if you are having any question, you can ask. You can write your question in chat box also.
Hello, sir.
So,
ma'am, I'm audible?
Yes, ma'am, you are audible. You can ask question.
Yeah. Good morning, sir. Saito, sir.
Good morning.
I'm audible, sir. Yeah, this is Maheshwari. Actually, sir, it's a very clear and explanatory part of demonstration. I just want to ask you only one thing. All these things, it is controlled fully in the remote, that is in the software. In case if there is any network issues, because possibly it happens when you move towards any interior region, is it possible to cover for all the parts of the world?
Dr. Saito, just for clarifying the question, that the madam is asking whether it is possible from any part of world, means like one question more that somebody asked, can we access from Sudan? Other than
Sorry, I didn't get that. I'm not good at speaking English. So, Fuku-san, please answer this question.
Of course, our system can use for all the world. So you only have Zoom ID and internet, and of course you should be trained how to use the equipment. That's all.
Yes, because if your internet and your net package, it is very high only, these things are possible. Yes.
So you can see today, Dr. Rani can use Zoom to control and use to analyze this PS device in our center.
Yeah, it's really interesting, sir, because somewhere from Japan, we are able to control here in SRM Ramapuram. It's really an excellent thing, and it's really a very good platform also. Thank you, sir. Thank you so much, sir.
So thank you very much for your attention.
Thank you, sir.
Thank you, Fuku-san. I'm sorry.
Hi, so I saw some question in chat box.
Thank you, ma'am.
So how can we send our sample for remote accession? Of course, you should send the sample to our center. We should set up and prepare something. After that, we will give you your permission to remote control. After that, we got data and send back to you data and your sample.
Yes, I would like to add to Dr. Thai that before you send your sample, you have to get training on the system. Then
Yes.
only you can get access.
Yes, of course.
And as in the beginning, Dr. Saito mentioned that there is no operator, only the students are operators. So in that case, you have to learn the system first before
Yes.
sending the samples.
Yes, yes, yes.
Am I right, Dr. Saito? Am I explained correctly?
Yeah. Please send the sample, and so I said no operator, but technical stuff is there. There are many technical stuff. We can teach you how to use by using internet.
Yes.
So for example, today is I present to you how to operate, but the senior technique is Dr. Ueno-san. He is well known and had much experience.
Okay.
So yes, he will support about experience.
Okay. Any other questions? Participants? Okay. If there is no more questions, I would like to thank Dr. Saito and his team, Dr. Thai, and other professors for showing us a demo of XPS and TEM. And thank you for very much, sir, for showing this demo. And we are very thankful. The session was very interactive and interesting. And hopefully it will be helpful for our all participants. Thank you, Dr. Saito and team.
Thank you very much.
Sanju ma'am, thank you, Dr. Saito and his team for the detailed demonstration of remote controllable analytical equipments. Thank you, sir. And thank you, Sanju ma'am. And now I request the participants to fill the feedback which is shared in the chat box. For session 5, the feedback is shared in the chat. I request all the participants to fill it. Dear participants, you can join in the session 6 at 1 p.m. today with an invited talk of Dr. Rajabhupati Mani from Aalto University, Finland. So there is a contributor session, parallel session going on. You can join in that session in another link. The link will be shared now.
Dear participants, the link of oral presentation is shared in the chat box. Please join the oral presentation by using this link. It's going on now. Dear participant, I will repeat again. The link of oral presentation is shared. Yes. Someone asking something? Yes, there is feedback link in the. There is feedback link. You can fill the feedback for this session. It is already shared. And now we have shared it again. Please have a look on a chat box. You can find the link of feedback form as well as, yes. Yes.
Ma'am, where can we post a poster presentation, ma'am?
So
Black
there,
or mid?
okay, so I have shared the link for the oral presentation, and there will be Slack link which we have shared you earlier. Or for more detail, just I will come back to you. Just
and Sanju ma'am, who is a student who is asking that?
Yeah, please tell your name.
Akshaya, ma'am.
Akshaya, can you
Poster number 33.
Poster number 33, Akshaya. We'll call you back. Okay.
Ma'am, it's not connecting.
Yeah.
We will call you, Akshaya. Akshaya will call you.
Ma'am.
Akshaya, are you in the meeting?
Yes, ma'am.
Yeah, we will
Yes,
call
ma'am.
you. We have your number. We will call you.
Yes, ma'am. Thank you, ma'am.
To help you. Okay.